We'll call this energy part 1. Okay. And I want to start with the qualitative side of energy. The conceptual, just what is it? How does it connect with day-to-day stuff? Where do you see it? And so on and so forth, right? So let's just start with a definition for energy. How would you define energy? What is it? Say it a little louder. Okay, used to create forces. Getting there. Okay, let's clean that definition up a little bit. Used to create forces, used to do something. What makes things happen? Okay. Let's keep going. I think we're kind of. Let's wordsmith that a little bit. The thing that makes things happen. Yeah, Paul.
It's like a property of objects that like gets converted to what it can be used to.
Okay, so a property of an object that allows it to make things happen. Okay, so let's go with that. I think that's kind of neat. Property of an object. I like using student definitions because I think that provides ownership. I think it sticks with you better if it's something that you've made up. Property of an object that lets it make things happen. Cool. Any other ways to phrase it? Any, do you guys feel like there's anything missing in that definition? If they said an object has energy, and then you looked at it and said, okay, well that means that it has something that lets it make things happen. I think, sure, Mark. Ability to do work. Okay, so now we'll have to define what does it mean to do work. What does it mean to do work? Or, okay.
Like the ability to cause an acceleration.
Say again?
Ability to cause an acceleration.
Ability to cause an acceleration. If I have a battery, would you say a battery has energy in it? It stores energy, right? And I plug it into a computer, is my computer accelerating? No. So there's energy there, but it doesn't necessarily have to be accelerating, right? Yep.
Ability to change your surroundings.
Ability to change surroundings, I like that. Okay, ability to change its surroundings. I like that. That's good. I think that's really important because that implies that there's an ability to interact. Okay, so not just that it will do things on its own, but that it can influence other things. That energy is something that can transfer, right? And so you can talk about energy deficits or surpluses, right? It gains and loses, and it suddenly becomes this currency, so to speak, that can go around. I think that's good. Anything else? I think these are pretty satisfactory definitions. So good. Here's the thing: as we go into this unit, and I think with a lot of physics too, there is like our we've grown up living on this planet for whatever 17, 18 years, 16 years, or my 30 years, and we have our daily experiences. And then we take a class like physics, and it's like, well, actually, all the rules are this number, this number, this number. And there could be a disconnect between what we experience from day to day and how things look on paper. Okay? And I don't want you guys to get that disconnect. Everything that we do in this class, you should be able to come up with a real-world scenario where you can see how all the physics is playing out. So it's the same thing here. The ability to change its surroundings, anywhere from like a battery that runs a motor, or maybe it runs your screen, or it makes calculations in your computer, or from chemicals in your car that you ignite to release energy, and you manipulate that energy to run your motor and move your car, right? That's changing your surroundings, or at least its surroundings, whatever it is that has the energy, right? Cool. So what I want to do is start thinking about have you guys think about the different kinds of energy that you experience or know about, right? In the same way we categorize forces, we had normal force and elastic force and friction force and so on and so forth. We can do the same thing with energy. It's not that these energies are different fundamentally, it's all energy, right? They're all transformable from one type to another, but it's very convenient to categorize them so that we can describe them, we can create models for them and so on and so forth. Right? So, what kind of energies do you know? What are the different forms? Yeah. Light. I will call that electromagnetic energy. How about we'll do electromagnetic / light. Because we know there's visible light, but there's also infrared, microwave, ultraviolet. There's all these different bands of electromagnetic waves. They all have energy in them. Sure. Yep. Heat. I will call that thermal energy. Paul? Elastic. I'm going to put that over here for a very particular reason. Actually, let's just stick with just the name. Elastic, yep. Chemical, I'm going to put that right here. This will all make sense in a second. Yeah, what? Kinetic. I'm going to put kinetic right here. Okay, kinetic energy. What else? Yep. Potential. Okay, so I'm gonna. The reason why I kind of save some space here is because I want to put potential as a parent of elastic and chemical. Because when we look at elastic energy, what we're really talking about is an elastic potential energy. You store energy in the bending and stretching of an object. Where you have chemical potential energy, you store energy in the bonds breaking or forming in molecules. What else? Yep. Nuclear energy. Okay. Good. I guess you could possibly even argue it's like a nuclear potential energy because it's. But we'll just say we'll just put nuclear off to the side. What else? There's more stuff. Yep. What? Mechanical. I'm going to put that in the middle here because mechanical is also kind of like a parent term. There are things that fall under mechanical energy, like kinetic energy or elastic energy. By itself, mechanical energy is an overarching term. Anything else? Yeah. Say friction?
Yeah.
Friction. Interesting. Friction as an energy itself. What does friction do? slows things down, right? So you initially have kinetic energy turns into what? Heat, thermal energy. So friction, I wouldn't say is itself an energy. It'd be hard to say like this object has frictional energy. It's more a process where kinetic energy is converted into thermal energy. Yeah, Paul. Gravitational energy. Good one. Gravitational potential energy, right? The energy stored in keeping things elevated, like a hydroelectric dam. Water falls down, we extract that gravitational potential energy. What else? Sound? Sound. I will put that under wave energy because it doesn't have to be in air, right? It could be in water, whatever. The waving of an object, which is also a mechanical energy. Actually, gravitational would also be a mechanical energy. Mechanical energy is usually associated with a bulk object. You'll find that like chemical energy, chemical potential energy is in the electrons, right? It's microscopic. Same thing with nuclear, it's in the protons and neutrons. But when you talk about kinetic, wave, elastic, and gravitational, you're looking at the full-on object and what's happening with the bulk physical object. What else? Anything else? Yep. Solar energy? Well, that would be like electromagnetic or light, right? But that's good. I think you can kind of see how it's starting to get useful to be able to categorize different types of energy into these well, whatever categories. There's one that's missing on here that we use all the time. It revolutionized society in the mid-1800s. Electrical. Electric energy. It's kind of hard to say whether it's potential energy or just not. It's kind of both. So I'm gonna put a star next to it because you can have electricity that's flowing, right? And that in itself is has a lot of energy in it. You know, when you have lightning and the electrons actually flow, there's a lot of energy there. But there's also that energy had to come from somewhere. It was initially stored in the separation of them, right? It starts potential, and then it releases in a current. So it's kind of both. You can have electric potential energy and then turn it into just normal electric energy. Yep. So electromagnetic is in the wave, when it's in a wave. So like when electrons change energy level, right? They release photons. So electromagnetic is really in the photon and not really in the electron itself, right? So when we talk about electric energy, that's like the electrons flowing through a wire in the outlets or in your computer, right? In the circuitry. You don't really have electrons zipping around in space, right? But when you talk about X-rays and gamma rays and ultraviolet and light, visible light, these are photons. Photons that are frankly can be pretty hot. If you sit in front of a fire, the fire is not literally spitting molecules at you that hit you and make you warm. It's actually just the radiation. It's the infrared light that is really warm and it's giving off a lot of it. So that's why you can have a fire behind a glass pane and it's still very warm. Any other energies? I think that's pretty much all the ones that the other class got. If you can come up with another one along the way, we will throw it in there. What I want to do is just want to spend a little time, defining these is not, the definitions are not going to be on the AP exam because on the AP exam we only do mechanics and E&M. So you don't really need to know thermal energy, you don't need to know nuclear energy. However, it'd be really unfortunate if as an AP Physics D student to go on not knowing at least on a surface level, what a lot of these are, being able to define them. So I want to make sure that at the least, I think it's my responsibility to make sure that you guys are able to define these, having studied physics. So let's start with the easiest one. What is kinetic energy? How would you define kinetic energy? What? Energy and motion. Perfect. Super easy. Cool. How about, let's go through these different potential energies. So how about gravitational potential energy? How would you define it? What is it? What makes something gravitational potential energy as opposed to something else? This one's can be kind of hard to define. I'll put it this way. Let's just kind of compare and just think of some scenarios for a second. I take this pencil and I lift it up, right? I put energy into lifting it up because gravity is opposing me and it takes my effort to lift it up, right? So as I lift it up, it now has energy because when I let it go, it falls. So clearly the influence of gravity is important, right? If I was on the moon, where it's like 1/6 the strength of Earth's gravity, it would take a lot less energy to lift it up. And when it falls, it would fall and release a lot less energy as well, right? So gravity must have something to do with it. If I take this pen as opposed to this textbook, the textbook requires more energy to lift up, right? So there's more energy in the textbook because it has more mass. So the mass has something to do with it as well. And also the higher I lift it up, right, the more it will release on its way back. So something to do with the influence of gravity and its weight, or really primarily the influence of gravity, its mass, and then kind of its vertical position, right? So let's try putting it all together. Let's say an energy associated with the vertical position of an object influenced by gravity. So the influence of gravity is pretty important. I mean, if there was no gravity, well, there'd be no gravitational potential energy. This idea is also very useful because later on we'll look at gravity as a field, kind of as a influence of space, and there's another force that influences the space around it in a similar way, which is electricity. An electric field behaves very similarly to a gravitational field. So just as there's an electric potential or gravitational potential energy, there's an electric potential energy. And it's kind of nice to have that parallel. Okay, how about elastic potential energy? How would you define elastic potential? Sure, what?
Energy associated with the stretching of the object.
Or compression, right? Or compression. So we can generalize it more to like the deformation of an object. Okay. So it's not so much that it just has to deform though, right? Because I can take silly putty and I can squish it, and it, there's no elastic energy there. It has to want to go back to its original shape, right? So a mixture of those. So let's see. An energy stored in the a more technical term is the strain. When we talk about strain, is a measure of how much an object has changed shape relative to its original shape. So in this strain or deformation of an object, also that can return to its original shape. Okay. So kind of an interesting aside from this or example of this is, some metals, when you bend them, they want to go back, right? And you bend them, they can store energy, and when you let it go, it moves back. If you bend certain metals and they don't want to go back, that energy needs to be released some other way. And actually, if you bend certain metals, like very strong metals, and you put a lot of energy into bending them, and they, twist and turn, and the molecules have to adjust shape, they can get pretty warm. They can actually get pretty warm or hot just from the permanent changing of their shape. So if it can't store that energy, or in other words, this is kind of evidence for elastic potential energy, is that if you bend it and it can go back, it can get warm, but not as warm as when you bend it and it doesn't go back. That energy really has to get released in a different way. Okay, how about chemical potential energy? AP Chem people, how would you define chemical potential energy? Sure, Drew.
It's like forming or breaking bonds and then using energy.
Okay, not always losing energy, right? Sometimes you have endothermic reactions where you form a bond and it absorbs energy, or it can release energy. But good. So let's see. Energy in the forming or breaking of chemical bonds. Now, I want to be a little specific here in that when we talk about chemical bonds, all chemical bonds, I mean, why do chemicals want to bond? Why do elements bond with each other at all? What causes them to do that? Stability? Stability in which part of the atoms? What part of the atom is doing all the arranging and rearranging? It's the electrons, right? At the end of the day, it's always the electrons. When we talk about chemical bonds, right, as opposed to nuclear bonds or nuclear reactions, chemical bonds and chemical reactions are always involved in the electrons. So when you talk about forming or breaking chemical bonds, really what we're talking about is the rearrangement of electrons to different energy levels and energy states, right? And they're always trying to reach a minimum or a stable state. Sometimes there's an activation energy, right, in order to get them to a lower state, but in the long run, right, in a general sense, is a rearrangement of electrons. So I want to put an asterisk there to kind of think about electrons. Right, that's the focus when we talk about chemical bonds. We're really talking about electrons. Okay, how about electric? Let's talk about electric potential energy before we talk about actual just normal electric energy. How would you define what creates electric potential energy? Electricity. So what is electricity? I wouldn't consider that electricity, right? If the electron stays within the atom itself and changes shells or changes energy levels, it releases photons, but I wouldn't really consider that electricity because that implies that you can have electricity of just one atom. That's not really usually what we think of in terms of electricity. Electricity requires more than just one atom. It requires the electrons to do something else. Yeah.
Electricity is just the movement of electrons.
Okay. So it's like a flow of electrons, right? They need to move around. When we talk about electricity, you usually have a circuit, and the electrons have to flow through, right? But that's still not really electric potential energy, right? How do you store the energy? Yeah.
Well, you would store electric energy by like having an object that had a lot of extra electrons, and then it wants to move to a place with less electrons, and that will cause movement of the electrons.
Good. So it is a imbalance of charges, right? An imbalance of charges or a separation of charges. So if you think about lightning, right? It is not just that there's a lot of charges in the clouds and a lot of charges on the Earth. It is that they're imbalanced. That's why they want to come towards each other. So where did I put it? Energy stored in the separation of charges. Okay, if there's no imbalance, if it's neutral, there will be no reason for the electrons to move around. Okay, so we got elastic, chemical, gravitational, electric. How about thermal? We hit all the potential energies. How about thermal energy? What is thermal energy? Really trying to take your background knowledge and clean it up, make it more precise. What is thermal energy? Sure, what?
It's like the movement of atoms and molecules.
The movement of atoms and molecules. Why don't you be more specific, or let's be more specific. Because I can have wind, and that's movement of atoms and molecules, but I wouldn't call that thermal energy in the wind, right? Yeah.
Like the speed of movement.
This.
of those molecules.
But again, you know, if I compare wind, if I have wind that is blowing a bunch of air molecules in a certain direction, I wouldn't say that the energy in the wind is its thermal energy. Because you can have cold wind, you can have hot wind. What is it that I'm identifying when I say it's cold or hot? What is that really measuring? Because that's really what we're talking about when we're talking about thermal, right? We're talking about, is it cold, is it hot, is it 100 degrees, is it 20 degrees? What is it that I'm measuring when I say it's 100 degrees Celsius or 20 degrees Celsius? Heat? Not exactly. You can have two objects of the exact same temperature, this book and this metal pipe, in the same room at equilibrium, same temperature, but the pipe will feel colder than the book. Right? It'll feel colder. You will experience more heat loss to the pipe than you will feel to the book, even though they're the same temperature. So it's not heat. You're measuring something else about the temperature. Yeah, Tatiana. Temperature difference? Yeah, but what is temperature then? I guess that's really what we're trying to get at, is when we're talking about the thermal energy, we're talking about this temperature energy, right? We're kind of getting there. Trying to get you guys to really dig into misconceptions. How about, let's put it this way. Let's say I have a piece of metal and it's solid, and we know that objects in a state of in a solid state, the molecules or the atoms cannot move around. Right? Generally, they're in a crystal structure or a lattice or something like that. The atoms cannot move around, so they can't, fly around, not like gas molecules. But we still say it has a certain temperature. You can have a red hot piece of metal that's 1,000 degrees Fahrenheit, and it'll start to glow and all this kind of stuff. What's happening to the molecules when it gets hotter and hotter? The atoms. Any ideas? You guys didn't learn this in chem? Yeah, STEM chem? How about this? Let's think of it this way. As you take an object like metal and it gets hotter and hotter, especially if it's pure metal. Well, I guess it doesn't really have to be pure. It could be an alloy. But as it gets hotter and hotter, it goes from a solid state to a liquid state. And it transitions very smoothly. At a certain temperature, its structure starts to break down and it becomes more malleable, so on and so forth. Okay, sorry, good.
Describe the bonds between the molecules.
Yeah, the bonds start to sort of break. I mean, they become dominated by something else. Is really what's happening. Why? What do you think? Oh yeah, the bonds start breaking down because it's not so much that the bonds just disappear. It's that they're no longer strong enough to keep them from starting to move past each other, right? So as you put more energy into it, the molecules themselves start to be able to move, which means that from the beginning they were able to move a little bit, just not enough to overcome the bonds between them, right? So the temperature then is a measure of how much molecular emotional energy you have, but really in a random sense. Okay, it's important to recognize that it's an average random kinetic energy in the atoms and molecules. So when you look at wind, it's a bulk movement. It's a bulk movement. Everything is moving in a certain direction, but within that, the molecules are still bouncing around in a random way. And how fast they're bouncing around in a random way, that is what we're measuring with temperature. So when you have a solid, the temperature is a measure of how much they vibrate. The hotter it gets, the more they vibrate. When it starts to vibrate faster or with more energy than the bonds can hold them, they start to slide past each other. Then it turns into a liquid. When it gets hotter than that, they start completely breaking bonds from each other and they become a gas. And they have too much energy. They no longer just vibrate, they full on fly around. Okay. So thermal energy is the average random. It's important to note that it's random. It's random so that you don't have a net movement in your object or your material. Of course, if you talk about a gas, you know, it will diffuse. Same thing with fluids, they'll diffuse. You should have learned this in chemistry too, right? The hotter it gets, the faster it tends to diffuse throughout a room because they move faster. They move faster and they kind of disperse themselves faster. So the average random motional energy at the molecular level. That's important to distinguish. So when we talk about kinetic energy is a bulk motional energy. When you talk about thermal energy, is a molecular random motional energy. And it doesn't even have to be translational. Complex molecules will vibrate. They will rotate. They can rotate across different kinds of axes and directions. And all of those are different modes for storing energy. Okay, so as you heat something up, if you study this very carefully, more complex molecules can have different specific heats. It really is kind of goes into describing why different molecules have different specific heats. It's how it can store the energy that you put in order. So if it has a lot of different ways to store energy, then it won't actually be moving around. Temperature really does measure specifically its translational energy. And so if it can store it in other ways, then you have kind of different modes for thermal energy. Okay. I think, let's see. When are we out? We're done at 12:35. Okay, so we're gonna move on. Okay, we spent a good amount of time on this, looking at different kinds of energy. We didn't talk about nuclear. We didn't talk about wave, and we didn't talk about electromagnetic. We'll try and get to those at a later time. There's a couple of concepts that I really want to try and get to today, but it's important that you guys are able to distinguish these. Okay, so these are all actually in the book too. Wave energy, I think, is in like chapter 15 or something like that. The thermal energy, there's a whole chapter 16, 17, 18 is on the kinetic theory of gases and like how you can determine the definition of temperature, derived temperature. Electromagnetic, we'll get to, that's like chapter 35 after it goes through electromagnetism and nuclear energy. There's the whole modern physics part of the textbook. The book is really good. It has all this stuff. If you really want to look into it, it's all there. All right, so I want to continue on then into a different perspective of energy. Okay, a very general concept of energy is that energy is like a thing, like a currency that objects can exchange with each other. Okay, it's not physically there in the sense that it's not like matter, where it's not exchanging matter, but it's exchanging something sort of intangible, and we call that energy. So energy is measured in joules, named after a guy. I think his name was James Joule, some long time ago. 1 joule is equal to 1 Newton meter. Sometimes it's also written as 1 kilogram meter squared per second squared. Any of those three are a measure of energy, which you'll notice that this is very similar to the unit of measurement for torque. Torque is also a Newton meter, but you will never talk about torque. You'll never measure torque with a joule. Okay, so joules is very specific to energy. So you really have to look at the context of the problem. If it's talking about turning things, rotating things, and twisting and turning, that's probably torque. You just use Newton meters. Or in English units, you'll use foot-pounds. Foot-pounds can be used to measure, foot-pounds of torque. Whereas when you're talking about energy, you're going to use joules. Energy is also sometimes measured in calories or BTUs. There's a lot of different ways you can measure energy, but we'll be using joules for this. What was BTU? BTU stands for the British Thermal Unit. It's because they want to be special, I guess. I don't know. Okay, so when we look at energy, a good way to diagram how energy moves around is with this diagram. You have a system, and you have its environment. Okay, so the environment is usually considered to be just this, everything else. You have a system, the thing you're considering, but let's say it's your car, or if it's the ecosystem, or it's the earth, or whatever, right? There's the thing under consideration. And then an environment is just everything else around it. And generally it's understood that the environment is like this infinite reservoir of energy where it can provide as much energy as you want, or it can receive as much energy as you want. It doesn't really matter. You're not caring about what the environment can or cannot do. You're more interested in how it's interacting with your system. So you might have energy transfer. So I'm going to put energy transfer with a question mark. That says transfer. And the idea here is that energy, like momentum, is conserved. Okay. What was it that made momentum conserved? There was a very specific law that resulted in the conservation of momentum. You guys remember? Newton's third law. Okay, Newton's third law was the reason why momentum is conserved, because for every action there's an equal opposite reaction, so on and so forth. Pretty much, it's kind of the same way for energy. It doesn't really come from Newton's third law as much, but if you study thermodynamics, it really is one of the fundamental laws of thermodynamics that energy is conserved. Meaning that whenever energy transfers, it will never like grow like an investment. Like if something gives 10 joules of energy, the other object won't suddenly somehow gain 12 joules of energy. It's very direct, right? There's no like interest rate and so on, whatever. Also, if there's no energy transferring, then the energy of your system should stay the same. So I actually kind of like this definition for the law of conservation of energy. Okay, when we talk about the conservation of energy, what we mean is that it cannot be created or destroyed, but more so if no energy transfers in or out, in or out. If no energy transfers in or out of the system, the energy in the system will be constant. It's a really important concept because what that means is that if we look at a system and we see that energy is either increasing or decreasing, it must be interacting with its environment somehow. Okay, it must be. It must be gaining it from somewhere, it must be losing it from somewhere. So if we look at the Earth, Earth is this big old giant thing. We think it's the ultimate system. There's nothing going in or out. But that's not true. It gains all its energy from the sun. Right? Okay. Questions about just conceptually how energy works, or from your own experiences about energy? Conservation of energy. Okay, so colloquially, I think, from everyday experiences, when you talk about conserving energy, we usually talk about it in terms of don't use so much energy. But it's kind of a misnomer because you don't use up energy. When we consume energy, it doesn't mean that it is lost and gone forever. There's this idea, this kind of, the way we use it in our language is like when I use up the electricity, right, from using my computer and using my TV, it's like that energy is just like destroyed, consumed, used up. But it's not. It's just transformed and transferred to other things. Most of the time, it's transformed into heat or light. So you use your iPad. It's lost in heat because the circuits are in the middle of making processes, switching ones and zeros or storing electrons moving around. It turns into heat. It's lost. It's lost in thermal energy. And then you have a screen, right? And so there's the screen, there's the speaker, it's moving this diaphragm. There's all this stuff going on that's transforming the energy into something else. Okay, it's transforming it. It's not consuming it, right? It's just that usually when you transform energy into heat or light, it's really hard to get that energy back. That's what we mean when we say it's used up. It is now turned into a form that is not useful for people. Okay? But we have ways of transforming energy. That really is what makes humans different from like every other species on the planet, is that we can create tools that manipulate, going back, ability to change its surroundings. We can manipulate energy. We can turn thermal energy into mechanical energy, right? We use heat to boil steam. Steam gets hot. We make it run really fast. We make it turn a turbine. We can turn chemical energy into mechanical energy. We have a car. We blow it up. We make it, again, turn. Most of the time, you'll find that anytime we convert something into mechanical energy, we take it and then we make it turn something. Like electric motor, we make it turn something. Your chemical, internal combustion engine, we make it turn something. So anyway, okay. So the last thing I want to do off of these notes, I want to now approach some of the math side of it. Okay, so here's the thing: when you look at the math side of this stuff, I really don't want you to lose sight of the conceptual side of this stuff. Okay, so when we look at all the math, it's gonna seem like none of this is related at all. Okay, don't do that. It is. It's just looking at the numbers. This is just, conceptual side. Okay, mathematical side. So let's look at the mathematical side. In order to look at the mathematical side, we have to define work. Okay. In order to talk about work and to actually derive some of this stuff, now in the book, chapter 10 kind of is gives you a lot of the equations right away. It doesn't really derive them, and then in chapter 11 it derives them. I want to start with the deriving part, okay, because I think it will help supplement your understanding of this material. But in order to do that, we're going to have to use a little bit of calculus. Okay, so kind of like with momentum, when we looked at that calculus, we just want you to understand the meaning behind that calculus. You don't actually have to make any complex calculations with it. Okay, so my understanding is Calc AB people, you guys have done derivatives now, right? Okay, so when we look at Newton's second law, and it's kind of funny that we always start with Newton's second law, but that's important because you'll see that this isn't really a new law of the universe that we're going to be deriving here. What we're seeing is that it's just another perspective or outcome of Newton's actual laws of the universe. So, from here we can say that, well, if the net force is equal to mass times acceleration, let's look at it in terms of the velocity. Okay, so your acceleration is, more specifically, a change in velocity over change in time, right? A dv dt is the instantaneous rate of change of velocity, right? What I'm going to do here is a math trick. Well, not really a trick. It's I'm going to use the chain rule. Okay. It's funny. All the class.
Oh my god.
Okay. So
Warner's legacy carries on.
when I use the chain rule, what I'm doing is I'm going to look at not how the rate of change of velocity is influenced by a change in time, but how the positional changes are associated as well. So I'm going to do dv dx times dx dt. Okay. So you look at how the chain rule is applying, and again, actually, Calc A people, have you guys done chain rule yet?
Yeah.
Okay, so you've all done chain rule. Okay, cool. That's really nice. So, in other words, what we're saying is that if there is a positional change, right, a dx term, there must be some relationship between changes in speed as it's moving and how it's moving with respect to time. And that relation is mathematically equivalent this way by taking that product. Okay? So in other words, when you accelerate something, okay, its speed changes over time. But what this is identifying is that in order to change your speed, you must also change where you are at. You must change your position. And how your position changes with time and all that stuff, there's a connection between the position and time connected to all this acceleration and stuff going on. So this here is just your velocity, right? So what I can say is that the net force is equal to the mass times velocity times dv dx. So I'm looking at how my velocity changes with respect to changes in position as opposed to how my velocity changes with changes in time. Okay, so from here, I'm going to separate it out. I'm going to move the dx to the left-hand side so that I can integrate. Okay, I just brought this over. Okay. So again, this is kind of a technique of calculus where if you want to look at how the net effect of these changes, you need to use an integral. Okay. Derivatives gives you the instantaneous value, and then an integral gives you a net effect, right? A sum of these changes, these infinitesimally small changes. So from here, I'm going to integrate. So if I take the integral of the net force dx, okay, think about what this represents. All I'm doing is if there was such a graph of the position versus the net force, if this were a graph, and if something was being pushed and moved around and it's being pushed something like that, I'm looking at the area under this graph. I'm looking at what that means. What is the meaning of that space, that area under that graph? This must equal to the integral of this guy on the right-hand side. And for those, if you haven't done integrals yet, the meaning behind an integral is that it's the area under the curve is the net effect of these infinitesimally small slices that you're adding up. You're taking a really small slice of dx and you're saying, okay, what is the contribution of this force over that space? Right? That's what the meaning of the integral is. Mathematically, what you do with an integral is it is effectively like an antiderivative. It is the reverse of a derivative. So for example, if I said the derivative of what gives you x, the answer to this would be 1/2 x squared. And I want you to think about that for a second. What is the derivative of 1/2 x squared? The 1/2 is a constant. You pull it out. The derivative of x squared is 2x. So 2x times 1/2 gives you just x, right? So this is the integral of x dx. Okay, this would be the integral of x dx. So in the same way, what I'm doing here is if mass is a constant, then this becomes like a m times a 1/2 v squared. Whoops. Okay. 1/2 v squared. Now, because we're when we integrate, again, we're looking at the contribution, the sum of these effects over a certain amount of space. There's always going to be some sort of initial point and a final point. Some final and some whatever, whoops, like initial. Right? There's some initial and some final. In other words, over what amount of space are you trying to add up that area, right? And so we identify that this way. This is the notation. You draw a vertical line to indicate that you're looking at it. You're taking the difference between the final and initial spots, and so that you get essentially this 1/2 mv squared final minus 1/2 initial. Okay. More simply, you can just say it is the change in 1/2 mv squared. It's worth noting that we assumed mass is constant here, so that as you're looking at this change, your object isn't like spewing fuel or something like that. It's not a rocket. You couldn't really do this math if it was a object that's significantly changing its mass. But for most of the things you guys will do in here, it's fine. Like you're pushing a box, you're pushing a car, you're speeding up, whatever, right? So again, for the change in this. This should look familiar. What is 1/2 mv squared? You guys seen that before? This is what we call kinetic energy. Okay, 1/2 mv squared is the kinetic energy. Okay, so what we have here is the change in kinetic energy. We have the change in kinetic energy. Okay, that's the right-hand side of all of this mess. This whole mess, there were two sides to this. There's the left-hand side, where we put the dx over there, and there's the right-hand side. So you kind of split this there's the right-hand side, all the conclusions of the right-hand side, and you work that out, you get that the right-hand side represents the change in kinetic energy. So by doing this chain rule, what we've done is we separated that your acceleration must result in a change in kinetic energy. That's what this math is demonstrating. What we need to see is the left-hand side. The left-hand side is the cause of that change in kinetic energy. And that is this. That is your force applied over a distance. And this is what we call work. That whole thing. Work is this integral of the net force over a distance. Okay? So, and then this will result in a change in kinetic energy. Whoops. It's also worth noting that this is actually a net force, or sorry, a network. Your net work, your total amount of work done is equal to your effective net force pushing something over a certain amount of distance. And that is equal to the change in kinetic energy. This is called the work kinetic energy theorem. Okay? It means that in order to speed something up or slow something down, okay, in order to change its kinetic energy, you must do work on it. You must do work on it. You must apply a force on it over a certain amount of distance. If I push on this book right now, I am pushing on it, but there is no net force on it because it's not moving anywhere. And so I'm not actually doing any work on it. There's no work done on it. I can expend like bioenergy, my muscle energy gets tiring moving it or pushing on it. But if it's not actually changing place, it's not actually displacing, I'm not doing any work on it. It's not changing kinetic energy. It's not speeding up or slowing down. Okay. Any questions about this conclusion? What it means, what it represents, how do you get it? Okay, so you can get this two ways. You can get it if you happen to know what the force on an object is as a function of position, not as a function of time, as a function of position. This is very useful because it tells us how something has changed in its motion without knowing what's happening anywhere in between. Because it's not a function of time. None of this is about time. It doesn't have to be, you're not looking at a time graph. You're just looking at what is it doing at this spot and what is it doing at this spot. And, what is the, well, I guess the integral does mean you have to add up everything in between. But it's not as a function of time. So if you have that function, or if you can look at a graph, right? So if I give you a graph and I say, here's the force acting on an object, and it goes like this, right? You should be able to figure out how much change in kinetic energy it will have. This area is the work done, but it's also the change in kinetic energy. That's really the main usefulness of this, is that you can figure out how its speed is changing using that. So you don't have to use kinematics. You don't have to use, you know what I mean? You don't have to, that's one less variable to worry about. You don't have to worry about time. It's very nice to not have to worry about time. Okay. It is worth noting that this is the net force. You can have the work done by the work done of a specific force. And so we will write it like this. And I'm writing this very specifically as two vectors and a dot product. Okay. And I want to draw a diagram and kind of explain why that's important. If I have a box and it's moving to the right, okay, it's changing position to the right, and I push on it at an angle, like I push on it this way, right here. there is an angle between the direction I'm pushing and where it's actually going. This component of my force that's pushing downward doesn't contribute to its motion. And so it doesn't gain any speed in that direction. There's no actual dx up and down, which means that I can't really say it's the full force that's contributing to the kinetic energy change. The full force is not doing all the work. It's only this component that's doing the work, right? It is the component that is in line with the positional change. When we talk about dot products and cross products, we say cross products is the component of a vector that's perpendicular to each other. The dot product is the part of the vectors that are parallel to each other. So what we'll get is that the work is in this particular, well, it's kind of hard to write it out because we're making a couple different assumptions here, but oftentimes you'll see it written kind of like this. Sometimes you'll see it written like this. This is a very simplified scenario where F is constant and theta is constant. But technically, you should be using the dot product. What does that mean? Imagine this, okay? This is going to be kind of tricky to picture, but let's say you have a box and you're pushing it like this, but it's like going up and down a hill. So sometimes it's over here and you're pushing this way, sometimes it's over here and you're pushing this way, right? If you keep pushing on it and it's like going up and down, you're not always pushing on it in the direction it's moving. If this is the force, this is the force, this is the force, and this is the direction of motion, and now this is the direction of motion, and now this is the direction of motion. You see what I'm getting at? At each point along the path, your angle can change. Your angle can change, which means that actually when you do this integral, technically that changing in angle needs to be taken into consideration in your integral as well. Because you're adding up, you're supposed to be adding up every step of the way, your force times your positional change, your force times your positional change, every step of the way. So if your angle is changing, then your force that's actually pushing it along may change. That is the most complex scenario, okay? But that's really what the calculus is meant to do. It's supposed to allow us to consider the most complex scenario, even if we can't necessarily calculate it. Okay, that's why if you're in AP Physics P1, you will learn this one. This is the equation they see. Because they can't, when you're in P1, and if you don't use calculus, you can't take into consideration any sort of changes, right? Everything is constant acceleration, constant force, constant angle, constant everything. What calculus is supposed to let us do is it's supposed to allow us to consider instantaneous changes, variability, and that's important because that's what real life is. Okay, so this is a better definition for what work is done by an object at every step of the way. Most of the problems that you will actually see will look like this. I'll be honest. Most of the homework problems, most of the AP exam problems look like this. The force is going to be constant, and the angle is going to be constant, and then you're just looking at how far it moves. Right? One thing worth considering here is this is the work done by a specific force. So you could also have friction here. Then you can look at like the work done by friction would be like a negative F of friction, delta X or something like that. Right? Your force of friction would provide a negative work because it is pushing in the opposite direction of the positional change. If the box moves forward and the force is backwards, this is taking energy out of your system. It's negative work. Whereas this is putting energy into your system, it's positive work. Does that make sense? Okay. So when you look at this calculates the work done by a particular force. When you add all these work together, they should equal this integral using the net force. Your net work should match up with your net force. And then this is what actually gives your kinetic energy change. That's important to note. You can't equate this one to the kinetic energy change because this isn't the only thing acting on it. This is the net effect, which then therefore gives you the kinetic energy change. It's the same thing with like Newton's second law. Some of you guys made this mistake and you said, okay, the normal force from the platform gives you the acceleration. It doesn't, because it's not the only force. The net force gives you the acceleration of the platform, and then you can do that, right? So you kind of have to be careful. All right. I know this is all super conceptual, like super abstract. We will get to practicing it more later, but class ends at 35. And so we don't have that much time left to try any practice problems. Any questions about this stuff? It's a lot. Hopefully this stuff was pretty straightforward, but the math is pretty complex. And this is just part one. Okay, this is part one. There's a lot to energy. So, you know, the energy test is after Thanksgiving break. I wouldn't wait until Thanksgiving to start studying chapter 10 and 11. 10 and 11 are pretty dense mathematically. It's one of the more challenging mathematical sections that we've tackled so far. So you'll really want to take some time to study 10 and 11. Number 9, momentum should have been pretty easy.
Getting tested on these.
What's that?
9, chapter 9.
9 is also, it's going to be 9, 10, and 11 altogether.
I mean,